I get to introduce Stuart today. I am my introduction is going to be that I have been on Stuart's committee for quite a while, but I have rather suddenly adopted him. So he is going to tell us cool things about machine learning techniques for flash drought prediction. And I actually haven't seen all his slides yet. So, but I've been seeing his paper drafts, and he's got like 4 papers in progress right now. I think 3, talking about traditional drought prediction in CONUS, deep learning drought prediction in CONUS, and then looking at drought prediction across the world. So he's doing really cool things, and hopefully going to graduate this summer.
Yes. All right. Thank you, Dr. McGovern. Thank you, everyone, for coming. This is a talk basically, she said, going over most of the dissertation project over ability of machine learning to identify flash droughts. So just before going into it, I just want to give quick acknowledgements to the committee, to Dr. McGovern for taking me on this past semester and part of last semester as well as help pushing everything through, and Dr. Sarah for all the work he's done prior to help getting things done. So from there, we start, and basically just an overview or introduction of flash drought. These are descriptions of rapidly drying events. So for example, when we generally think of standard drought, those are drought conditions that develop on the long-term timescales on the order of months to years, sometimes in the decades, even for historical periods. But flash droughts develop very rapidly. You can go from normal to even above normal moisture conditions to droughts and to below the 20th percentile on the order of 3 to 6 weeks, sometimes even less. So this rapid desiccation can result in impacts on the ecology and landscape. The most common discussion of impacts is crop loss, but this drying out can also be discussed in terms of fire hazards, since that is creating basically a lot of kindling, among other things. So we'll get into shortly. But generally, research in flash droughts have been upticking in recent years, to the point we've gotten a general idea of how flash drought develops through basically this feedback where you have large demand for moisture in the atmosphere, which results in large transpiration from soils and vegetation. This dries out the soils, which increases sensible heat flux, since our latent heat flux is going down. That in turn increases the temperature and atmospheric demand, which basically continues to feed into this positive feedback that results in the landscape drying off at its scales. And the general conclusion from these is that in order to monitor flash droughts, a lot of the key variables that we want to do or that are involved in this loop are soil moisture that is being dried out, evaporation, which is how the moisture is leaving, as well as potential evaporation for the atmospheric demand. Other variables such as temperature and precipitation are also known to be key drivers, but these are the ones that people really want to, or are generally trying to monitor for flash drought events. In addition to this, further studies into flash droughts have developed a suite of different methods to identify these type of events. And they have generally begun to cluster around the idea of trying to quantify rapid intensification and drought conditions. So the way they generally work is they take some variables such as soil moisture, evaporative stress, and so forth, and then measure how fast does it decline within a 3 to 6 week period. And then if it's below the 20th percentile for drought conditions. And these different methods deliver sort of different flavors or perspectives on flash droughts. And sort of tangent to this, there's also been worked on recently is study of machine learning within traditional droughts. And in this case, machine learning has been used to sort of try to predict standard droughts. So these are long-term droughts they've been predicting on the scale of months to years. And they've traditionally been doing this by a regression problem. So they've been trying to predict things like SPI, standardized precipitation index, standardized precipitation evaporation index, and so forth. And they've generally found that tree-based models, as well as some density connected neural networks, have generally been most favorable towards this, to the extent that some of these machine learning methods have been able to keep up with and even in some cases outperform existing methods for predicting droughts. However, if we combine these two areas with flash drought machine learning, there is virtually nothing. There is, to my knowledge, one publication that is basically using machine learning to differentiate flash drought from standard droughts. But that is it, as well as some studies that were at AMS this past year, but that is the extent of it. So this is basically a large niche to be filled in order to sort of give a general idea on how these machine learning models can do with rapid drying conditions. In addition to this, for the idea of these global studies, is that there are not as many global studies of flash droughts. There's only about 4 or 5 off the top of my head, and all of these are basically looking at 2 or 3 different identification methods. Most of them tend to be focused on 2 regions. This map is basically showing for standard droughts, but if you were to take it for flash droughts, it's basically mostly the US and China, and everything else basically has a handful of papers at most. So there's a lot of focus on 2 regions specifically, not as much globally. So we're looking to take things to the global scale to help fill in that gap a bit as well. So, and this is our, basically the main research goals is identifying or determining how well can machine learning represent flash droughts. Since this is basically almost untouched concept, there's no real ground basis on how well machine learning can do in this topic, or what a good starting point would be. So this idea will basically be taking a bunch of machine learning methods and just throwing them at flash drought and seeing what they can do. And basically, once we determine which ones are doing best, expand those out into the global scale to see how well they can generalize to some of the heterogeneous patterns of flash drought. For example, flash drought has increasing trends in some parts of the world, decreasing trends other locations. They have different seasonalities. That is, different months where flash drought is more likely. So how well can the machine learning models adapt to that? And so going into the details, first looking at the regional scale for training the initial machine learning models. Data for the US was collected from the North American Regional Reanalysis, the NAR, and the data collected from it was averaged down to the pentad timescale, which is 5-day non-overlapping means. And it was collected from 1971 to 2021 with the focus on predicting flash drought within the growing season. Within the context of the US, that is defined as the time span from April to October, inclusively. And the variables collected for predicting flash drought are the 3 key variables we talked about before: evaporation, potential evaporation, PET, and soil moisture. Let's see what my cursor is. As well as with these 3 main variables, the pentad to pentad change in these variables was also determined. A 6 pentad or 30-day running mean was applied to those changes to sort of get a representation of rapidly drying conditions for the machine learning model to learn from. And some of the other variables with temperature and precipitation that known to drive flash droughts were also included for training. So when training these machine learning models, they're taking in these 8 variables and using those for making predictions. In addition, the machine learning models were verified or validated using k-fold cross-validation. And the idea behind that is that you take the data set and split it into k-folds. You reserve 2 of them, one for validation, one for testing, the remaining for training. And then that takes up 1 rotation. A separate rotation you take up where you reserve 2 different folds for validation and training, or for validation testing, the remaining for training. And you sort of repeat this until you've gone through all of the combinations of training, test, and validation. And this gives you sort of a statistical sample on the machine learning model's performance. For this study, I generally define the fall to be one growing season, since each growing season is about 4 or 5 months apart. So all the variables should be decorrelated from each other, which means each growing season should be statistically independent from the next one. As well as the fact that the data was standardized prior to going into the machine learning models. So, and next up is what are the models trying to predict? This approach was taken as a classification problem, wherein we have 5 different flash drought identification methods. Originally, we were planning to do more, to be more comprehensive, but then more papers with more identification methods came out, and this 5 was already proven to be a handful, so we stuck with these. And basically, the machine learning models are being trained to each of these separately. And so the 5 methods we're looking at were the methods published in the Christian et al. Paper in 2023. This is using evaporative stress to find flash droughts. The method in Nagard et al., which is using the SPEI, or atmospheric supply of moisture. The Pendergrass method, which is using potential evaporation, so it's measuring rapid increases in atmospheric demand. And the Liu and Natkin et al. Methods are both using soil moisture percentiles to identify flash drought. And these are the sort of frequency climatologies, which are how many years within the data set was flash droughts found. And these are sort of the climatologies that we want the machine learning models to be able to predict. We want them to be able to replicate these. And since we're basically going to be checking a lot of different machine learning methods at this has split into a couple parts. The first one is on standard machine learning algorithms, and by this is meant tree-based methods and support vector machines. The tree-based methods are basically random forests and ADA-boosted trees. So broadly, a decision tree is one that basically takes in a simple set of conditions. For example, is the soil moisture below 0.5 anomalies? If yes, go down one branch of the tree. If no, go down a different branch of the tree, and so forth until you arrive at a decision at the end. Random forest is an ensemble of trees, each perturbed to slightly different conditions, taking the most popular votes as the final class. And ADA boosting is also an ensemble. It's taking an ensemble of trees and then sort of perturbing the probabilities and thresholds of the trees to sort of boost the performance. The support vector machines for this study was using a linear kernel. You can use other types of kernels, but they generally did pretty much the same. And the linear kernels are much faster and much less intensive to run. So that one was used here. And a linear kernel is basically in a sense, a perceptron, which means all of the 8 input variables we have are multiplied by weights, summed together, and if that sum is above or below a threshold is what determines if there is flash drought or not. And the last point of this is that some level of XAI was also employed for this, basically looking for feature importance. This was done through 3 different methods. The Gini method is provided by sklearn, as well as the SHAP attribution permutation importance. They may not always be used because sometimes they can have a very hard time distinguishing these importance or contributions of each input, each of those 8 variables, as we'll see with the ADA-boosted trees. In addition to this, the skill of the machine learning models was determined by the true skill. I think it's also called the Pierre's skill score. Other metrics are often used, such as the critical score index, or the alcohol threshold score, ACC, and so forth. These were all looked at. They pretty much told the same story. The true skill score was used because it told the story with fewer decimal places. And so looking at the general performance, the values within the parentheses are the confidence intervals, so 95% confidence of the skill score. And in general, the ADA boosted trees were the best performing in terms of the overall scale, primarily for the Christian, Leo, and Otkin methods, random forests, and as the sport vector machines. We're doing better with the Pendergrass and Nagar methods, but overall, we're seeing dominance of tree boost. And for that reason, most of the figures shown in this section will be for the ADA boosted or predictions by the ADA boosted trees, since those were the best performing. And if we look at the composite mean differences, and these are basically the differences, or these are basically the true flash drought labels minus what the ADA boosted tree predicted. We're seeing a general pattern that's of over prediction. So large negative values as over prediction by the machine learning models within the hotspot regions of flash drought. So if we look at the climatology, we can see this more clearly. These are the frequency climatologies that are being predicted by the ADA boosted trees. And while there are regions where flash drought is more common, such as the Great Plains, such as the agricultural regions of the Corn Belts, and we can see the machine learning model is learning this spatial pattern, it is also heavily over predicting in these areas. It is also sort of predicting in other agricultural regions that are not in the actual flash drought, true flash drought labels, such as the Central Valley in California, the Snake Lava Plain in southern Idaho, or in some cases, the southwestern US. So we're seeing a lot of over prediction, in some cases under prediction where there is not a flash drought hotspot. But in general, the main concern with these climatology is sort of over predicting. And in terms of the seasonality of it, in some cases, the ADA boosted tree seems to be learning the seasonality of flash droughts. In some cases, such as in the Nagar method, such as in the Pendergrass method as well, is not necessarily getting the seasonality predictions quite as well. And if we look at the feature importance, so feature importance via the Gini method, the Gini method, and it's worth noting the Chap attribution and permutation importances are not shown here because for the ADA boost trees, those values were very small, like less than 0.01 in most cases. And it also had values that are pretty much identical for all input variables. So those were not necessarily delivering a clear signal. Or they're having those methods are having a hard time distinct or finding a signal. But the Gini method seems to suggest there is a dominance of soil moisture. With the Nagar and Pendergrass methods, the dominance is more in precipitation, but essentially it is finding that one variable is sort of becoming more important than all the others. The other variables contribute, but not nearly as much. And if we look back at our seasonality, we see that the ADA boosted trees is pretty much predicting the same sort of seasonality for all of these different methods. And that's sort of leads to are sort of suggesting that it may not necessarily be learning things about flash drought as much as it's learning soil moisture climatology. This being the time frame when soil moisture tends to rapidly decline during this climatology period. In addition to the overall climatology, it's also helpful to look at some specific events. So for example, 2012 is the textbook example of flash drought. It is the one that sort of spurred on a lot of all the initial investigations of flash drought as well, and started the whole field of study. It is was a fairly widespread event across the central U.S. That had billions of dollars in crop damages or crop loss. And generally, we see that the general coverage or spatial extent of the flash drought is fairly well covered by these machine or by the ADA boosted trees, by the random forest as well. When the identification method does not necessarily have contiguous patches of flash droughts, the machine learning model will fill that in. But what we are seeing, and this is helps us understand why the skill scores were very low. Like generally speaking, you see a skill score greater than 0.5, 0.6 and stuff. All of them were 0.3 and below. And we're seeing that with these different colors, it's showing that it is having issues with timing. It is basically identifying flash droughts often in the wrong month. So it's having this hard time getting the exact timing of when these events occur. There's another case study with 2017 that saw another widespread impact in the northern plains. And this is pretty much the same story. We're seeing generally the spatial patterns or extent of the flash drought is well represented. The machine learning model is definitely learning where the flash drought is, in some cases being overzealous, or in a number of cases is being overzealous, but it is struggling to get that timing of flash droughts, struggling to learn generally when they are occurring. And so just an overview of the standard machine learning approach is that the AWS trees were the best performing. They're showing some potential being able to represent flash drought in that they are learning the spatial patterns, the extent, or they're learning where flash drought is occurring, but they have limitations, and that there is some potential, there's overemphasis of soil moisture, so they're potentially just learning soil moisture climatology, heavy overpredictions in the hotspots and some agricultural regions, as well as struggling with the timing of these events. So that is the standard machine learning approach. And next up is the deep learning methods. So when we say deep learning, what we're basically referring to is a neural network with 2 or more layers. In this case, we're looking at a standard densely connected artificial neural network, as well as a recurrent neural network. The artificial network is basically one in which we have something similar to a perceptron we saw earlier. It is basically a lot of linear nodes. Each of the input variables are connected into each of the nodes. Each of those nodes are connected into all the nodes in the following layer, and so forth. So that hence the name, it is densely connected. Our current network has that dense connection, but it also learns things recursively in a time series. However, sorry, in this extension of that, you also have LSTM, long short-term memory layers, which are basically improving on a problem that recurrent networks have, and that they have, while they are trying to learn temporal patterns recursively, they have very short-term memory. LSTM layers are helping to improve that. And these are the network structures that were used for this study. In general, they had around, 2,500 to 5,000 parameters. Convolutional networks were also explored with this, however, had trouble getting those to predict realistic results. So they were sort of omitted for that reason. In general, the performance of the recurrent net or the neural networks as a whole, the artificial neural networks were struggling very significantly to identify flash drought. They were heavily reliant on the initial look at the feature importance for those was they're heavily reliant on like temperature and precipitation and basically learning patterns that were not very connected to flash drought. So it was having a very hard time learning those patterns, and the densely connected networks also struggle with some occasions that would converge on trivial solutions. The recurrent networks did not have that problem nearly as much. They were able to have much more comparable results to the AWS trees, also presented here for convenience. The recurrent networks were able to improve the skill on 2 of the methods, but not necessarily improve the skill on other methods. However, if we look at the actual predictions of the recurrent networks in terms of the composite mean differences and shortening the climatologies, we'll see that one of the issues that the AWS trees was having has been vastly improved on with the recurrent networks, and that is, it is doing much better with the over predictions. And if we go to the climatologies, we can see this. These are much more realistic climatologies. It is gaining flash drought predictions or frequencies on very similar orders of magnitude to what the actual labels are at. And some of the agricultural regions that the AWS trees were finding are not necessarily present in the recurrent networks. And so this is helping us suggest that the current networks is doing much more than just learning, for example, soil moisture. Is trying to combine these variables and learn something about flash drought. It is interesting that they also generally find or highlight this region in the southwestern US, because that is a region where you, for a hotspot of rapid intensification of drought conditions, but not necessarily flash drought. So it's interesting is picking those up, or still picking that region up as well. There is the caveat that is recurrent networks are obviously having a lot of trouble with the Otkin method. The fact that it's heavily emphasizing the southern US is very suggestive that it is over-reliant on potentially temperature and precipitation and is not necessarily gaining a whole lot. In terms of the seasonality, we are also breaking out of that soil moisture seasonality. And the recurrent networks are doing generally much better at trying to predict those. With some of the methods is getting that, for example, mid to late summer is the more favorable time frames for Nagar et al. Flash drought. It is getting the seasonality for some of the Christian et al. Methods. However, the one caveat to that is while you're breaking out of soil moisture climatology and trying to learn something different, sometimes you don't actually learn the correct thing, as in the Pendergrass methods and the Otkin method. So it's doing a lot better with the seasonality on some of the methods, but not necessarily all of them. And again, looking at the case study, this is 2012 was done again, just sort of as a direct comparison to the AWS trees. And we are seeing much the same patterns where it's learning where the flash drought is. It is sort of, or the recurrent networks are sort of reducing the over prediction of the spatial extent of flash drought for the Pendergrass and new cases. But in general, it is learning where they are, except for the Otkin method. However, it is struggling a lot with the timing again. This is an issue that's going to be very consistent. Timing of flash drought is very important, but that is one that is very difficult to learn, it seems. So, general overview of the deep learning results. Yes. Basically, what's already been said is that deep learning or the recurrent networks had comparable scores, improving some methods. They definitely improved a lot on the over prediction of flash droughts and the seasonalities. In some cases, they're breaking out of the soil moisture seasonality that the AWS trees seem to be stuck in. However, that can sometimes result in negative or not doing as well, such as in the Pendergrass method. So overall, what we're seeing is our two best methods are the AWS trees and the recurrent networks. There are some caveats to that, but from here, we want to take them into the global scale and see how well those are doing. And so or how well can they generalize? And so the global data was taken from the ERA reanalysis sets. These are the same variables as used in the NAR data sets. Was collected. There was some extra pre-processing involved since we're now working at the global scale instead of the just the US. And everything is still at the pentad timescale. These are the true labels, or the actual climatologies that we want the machine learning models to predict at the global scale. And we can see that these different flash drought identification methods do present different flavors of flash drought. For example, some methods heavily emphasize tropics. Some are more even throughout, but emphasize certain bands of precipitation gradients or moisture and energy gradients in the mid-latitudes. And they have different magnitudes and so forth. Now, in terms of more to do with pre-processing, this had to do with the fact that it's on the global scale. So we have different growing seasons depending on what hemisphere we're in. Northern hemisphere is still broadly April to October, but the southern hemisphere is September to March. Technically, it goes a few pentads say into April to make sure that it has the same number of pentads in the southern hemisphere growing season as the northern hemisphere. This is so the two data, or the northern and southern hemisphere, can be put together within the code. as well as there were some extra steps to make sure the global data set was actually small enough to fit on the home directory I have within the supercomputer for training. So this meant that the spatial scale had to be reduced from 0.25 by 0.25 degrees to 0.5 by 0.5 degrees. Secret points were removed again to keep the size of the data sets more manageable. And just as a general note as well, the global results for the current networks are still being tuned within the supercomputer. So we'll only be looking at the results from the ADA boosted trees here. And within that context, we can see with the ADA boosted trees, the scores generally went down significantly, with the exception of the GARA methods. In terms of the predicted climatologies, we can see that the ADA boosted trees are struggling a lot more to get the spatial patterns down. In some cases, there's just a heavy focus on the tropics. It is correctly getting that the ADA boosted or the LEO method is emphasizing tropic in its climatology, but it's kind of doing that at the extent of everywhere else. Or the machine learning model is basically learning that at the extent of everywhere else. In some cases, such as in the Pendergrass method, there's actually heavier emphasis on the poles than there actually is in the climatology. It is sort of like that as well within the GARA method. But basically, the only two methods that it is really getting sort of an even distributions of flash drought everywhere is the Christian and Odkin methods. And the Odkin method is doing slightly better with is much less under prediction. So that's the one we'll sort of be focusing on with the remaining slides here, although the others are available as well. And just zooming in some of the climatology, looking at the time series, this figure has a lot to look at. So we'll basically zoom in on a few of these because those time series basically has a few repeating patterns. In some cases, the machine learning model is getting the learning when drought is occurring within the broad time series fairly well, although this is very infrequent when it does this. In some cases, the times or the predicted time series has this curious U shape where it's predicting a lot of flash drought at the beginning in the 1980s and at the end in the 2010s, and then almost no flash drought in between. And then there are other cases where it is basically underrepresenting flash drought overall. And this is a standard pattern that I noticed with all of the predictions for each of the identification methods, is that very frequently it had this either U shape in the predictions or an inverted or bell shape, or inverted U or bell shape within the predictions, such as in the predictions for the Pendergrass method, where it's predicting all the flash droughts in, say, the 1990s and early 20s, or early 2000s, sorry. In terms of the seasonality, again, this figure has a lot to look at. We'll focus or we'll zoom in on two of the figures since this has basically two patterns where the machine learning model is basically saying flash drought is initiating either at the very beginning of the growing season or at the very end. And this may help explain why the machine learning model is having a lot of trouble representing flash drought. Is last time I saw where it was over or having everything at the beginning or end of the growing season is basically because it was overemphasizing one or two variables, and it was basically learning patterns within that variable. And this shows similar trends with predictions for the other methods. Sometimes with the LEO methods, most of the predictions were in the middle of the growing season, suggesting it's part of being heavily reliant on temperature, either temperature or precipitation for the climatology patterns. And the case studies these case studies I left in here. These are things we've already observed in terms of the machine learning predictions. In some cases, it's no longer getting the extent of the flash drought as well, but it's still struggling with the timing. But these are left in here as case studies for flash drought outside of the US, outside of China, because they also present other examples. So in this example, or other examples in something else. So in this example, the 2010 heat wave in southern Russia, this saw a flash drought develop within the southern part of Russia and basically had large crop impacts, especially as the flash drought extended further northwards later on into the growing season. And this also helped exacerbate the heat wave that was also going on. So you had a lot of impacts in terms of both crop damage, but also exacerbating the large heat wave that is being heavily impacting the health of the local populace as well. So these are additional set of impacts. Another case study that's given here is in the Amazon. This was a 2015 to 2016, more of a standard drought than a flash drought, although these methods all found that rapid development of drought conditions occurred in January of 16 into February. But these, again, have a sort of different flavor of impact in that this killed off a large number of trees within the tropics, the burning the burning of which saw a large increase of CO2 released, large amount of CO2 released from those trees. So this is, again, a different level or different type of impacts, where it's an environmental impact in terms of contributing towards climate change because of the CO2 release, as well as the ecosystem. And a sort of third case study, which is potentially a more serious one, is these droughts that occurred in Eastern Africa as well. This is an area of the world where, depending on the country, anywhere from 40 to 80% of the employment in those countries is based on agriculture. So when a droughts, in many cases, in some parts that began with rapid development, you can have this, oftentimes see this rapid intensification of drought that just leads into standards or traditional persistent droughts that basically destroys much of the crop. That has a large number of impacts in terms of the financial ability of that populace, since that's most of their working lives, as well as their food supply. This is an area of the world that experienced a large famine because of these droughts, and resulted in a large number of deaths as well. And this was sort of exacerbated more by the fact that many of the local governments did not necessarily help. And so this is also showing a sort of sociological interaction between the impact of droughts and the society. Each of these society can play a role in helping to mitigate these droughts. The US being a good example of how the Dust Bowl in the 1930s was very impactful, but the drought of the 1950s, which was arguably more severe, was much less impactful. So there's definitely help showing that there is a sociological level towards these impacts, and that is not equal everywhere. So just a broad scale summary of everything. Machine learning models showed some skill in being able to represent flash droughts. It was able to learn these spatial patterns, some of the seasonalities in terms of the current networks, or with the aid of boosted trees when those seasonalities ran closely with soil moisture. However, these still have limitations. They're struggling significantly with the climatology. There's still some overprediction of flash droughts. In general, the aid of boosted trees and recurrent networks were the best performing. It's also worth noting the performance of these flash drought, or the performance of the machine learning models, was not universal across all methods. Again, this is showing the strong heterogeneity in flash droughts. Each of these methods require different class weights to sort of compensate for class imbalance. And even then, you still get different levels of performance with each method, and sometimes different models are performing better. In addition, the aid of boosted trees struggled a lot with the global results, or global flash droughts, suggesting that in terms of using machine learning to predict these types of events, it may be better to focus more on the local to regional scale in order to get better results. The case studies also showed some different flavors of flash droughts. So these are different levels of impact beyond just agricultural loss, but that can lead into other impacts as well, depending on that interaction between the society and the impacts of the droughts. And it shows those are varying levels. So general suggestions for future works are not all flash drought methods, or not all machine learning methods were explored. There could still be more work done, for example, with convolutional networks that could help get those working and see some of the potential those have in predicting flash droughts. You can take different approaches. You can use physical constraints. These are purely statistical machine learning models. So you could try physical constraints. You could try breaking up some of these variables. One suggestion that had an AMS, for example, was taking potential evaporation and sort of breaking that up into its constituent parts with temperature, radiation, and so forth, and seeing if that helps the machine learning model learn some of the surface interactions better. You can incorporate things such as climate variability with ENSO and so forth. You could use a regression style approach to help look at these as well, such as predicting soil moisture or evaporative stress, and seeing how that does then with, or then using those to represent flash drought. And there are also general suggestions on investigating sort of these different types of impacts that droughts and flash droughts can have, as well as the looking to get a better understanding of how those societal interactions to help decrease the effects of flash drought, or the effects of both droughts and flash droughts, so it's less harmful to the society. So that is everything. Number of slides for references used throughout. So that's everything I have. Thank you.
And I will.
Okay.
You mentioned the soil what you
Mhm.
getting that at one level or
Multiple depths. So the way the NAR provides it is, I believe it has 3 depths that are average, 3 depths, like 0 to 10, 10 to, what was it? 0, 10, 10 to 40, 40 to 100 centimeters down. I am generally taking the top layers from 0 to 40 meters down, 40 centimeters down, 40 centimeters because that is generally the root zone soil moisture level, and averaging those together to get the soil moisture value.
have you looked further down? You're not looking to keep it down because it's still get a time lag. Maybe that time to not actually going.
It's very interesting. I haven't looked at the deeper depths. I've focused on 0 to 40 since that's the standard within flash drought for the root zone reason. But yeah, looking further down could be really interesting.
I have something that is kind of related. I just looked at the shape that you showed for the 2000, and how they were so different. Different subjects. Any, you know, kind of thoughts about why that might be. You've got
These ones. With these, I am not entirely sure why the machine learning is doing that. It's something I find very curious. I could understand it if it was focusing much more on the end of the time series, because then it's just sort of looking at climate change. But the fact that it also has this sort of U shape at the beginning as well as a curiosity, I'm not entirely sure what it's doing with that.
Yeah, I thought it was very curious, but I wonder what that